Okay. Good morning. This is our first seminar coming to you from the Fireworks Foundation, and we're doing this in cooperation with the PGI and the Western Pyrotechnic Association. And this morning we have a very good seminar coming to you from both Lithuania and Sweden. We have our presenters, Dominykas, Juknelevičius, and Alenfelt. And they'll be joined here shortly with two guests, Bob Winokur and Joel Baechle, who will ask some questions. This is the first of a series of some seminars we'll be doing probably every Saturday while we're in the COVID-19 crisis situation. And this is something that all of us pyros can do and pay attention and continue learning and sharing information around the world with each other. At the end of this seminar today, there'll be room for questions. If you're watching this on Facebook, you will have a little window at the bottom. You can ask some questions and we'll try to bring those together, a couple of them, and present those. If you have a question like that, keep it short so that we can transcribe it quickly and get it on to the presenters. So with no further ado, Dominykas, why don't you go take it away, and Per, and see what you have to say for today. Thank you.
Yeah, thank you, Steve. Can you guys hear us? Per, can you hear me?
Sure.
Okay, perfect. So again, my name is Dominykas Juknelevičius, and today I will talk about part of my PhD studies, which is on illuminating pyrotechnics. So this part of research is something that I did in Sweden together with Alenfelt, who is joining us today. And so let me just switch to my slides right now. It seems I cannot share the screen at the moment. We have to, Steve, if you close yours, I think then, yes. Okay, so we will talk about the part of the research that I did in Sweden, which was on the performance of red flare pyrotechnic compositions modified with gas generating additives. So we will talk about, this is generally, we will be talking about the publication that we recently published after this work was done and written up. So we have the publication in the journal called Propellants, Explosives, Pyrotechnics, published by Wiley. And so for those who are interested, feel free to look at the paper. And well, today we'll talk about different aspects of it, and most importantly, we'll try to also talk about how that is, let's say, interesting for the fireworks people, and what can they learn from this. So first of all, we'll talk about the hand flare in general and the experiments that we did, and later on we will continue talking about the the main experimental parts which we did. We will also show some videos. We will conclude, and after that we will have a question and answer session. So first of all, for everyone, just to get an idea about what we will be talking about. So we would like to first of all show a video of a performance of a hand flare. So you can see the chemical composition in the top left-hand side. And so you see the ignition, and finally when the camera adjusts the brightness, we see combustion of the flare. It takes around 60 seconds. The casing is made out of metal, and actually I have an example right here. This is more or less how it looks like, and the metal casing is does withstand the temperature, and for that reason we see it burning rather stably and the flame erupting from the chimney. And the experiment was performed in the wind tunnel, which you can see also in this video on the sides, the rounded shape. And finally, after decombustion, the body of the flare is glowing red hot. And that's it. We will come back to this video at the very end, just to take another look and perhaps give some more details about what we see here and why the flame is has the shape as it has here, and perhaps some more details about the sparks, about the luminosity, and some other details. So, okay, so when we talk about the flares, we talk about pyrotechnic illuminant compositions, and yeah, they have several applications besides fireworks, and mainly in distress signals. And there, perhaps you can add what kind of other uses are there for the, let's say, the illuminating compositions?
Well, we use them a lot, of course, in the distress signal business for hand flares and parachute flares. And in the military field, we use illuminating compositions for tracers, for shells and bullets. And there's also, of course, illuminating flares in parachute flares to illuminate the grounds. And this is all within the visible part of the spectrum. There also are invisible flares, near IR flares, but that is kind of outside of the scope here. So I think that's what we need to know right now.
Yeah, that's right. And I suppose in the brightest, the fireworks, especially the red and the green flame compositions that contain magnesium or aluminum, or a combination of both, they're kind of similar to the composition used in distress signals. Is that right, Per?
Well, the main difference maybe is that we use magnesium that is seldom used maybe in fireworks, especially in commercial fireworks.
Right.
But the principle is the same.
Right. Yeah. So, and talking about the hand flares, since they have a very specific use for as distress signals at sea. So there are certain parameters that that are quite important to mention, I think, that are for this particular pyrotechnic article. So first of all, it is designed to burn with the luminous flame of the maximum candle power, and I guess that's how they were designed in the first place, just to be as luminous as possible, so that, let's say if a ship breaks down and there's in such situation, when someone needs to call for help, the flare has to be as bright as possible. And yeah, so
maybe that is the thought. In the practical reality, there is cost involved too. So they just have to be bright enough, so to speak. That there is a demand for at least 15,000 candelas. But as you will show us, we now have compositions that can cram out far more luminosity than that.
Right. And in addition to that, it's also the flame color, and we will talk just in a second about the color purity, but it should be at least 80% or even higher, which is I suppose not that difficult for red flame pyrotechnic compositions, but more difficult for green and blue. But of course, there are also challenges that arise here. Then another parameter is burning with the minimum amount of slag, which is I guess the risk of let's say igniting the raft that when you use. Is that right?
Yeah, or maybe mainly that you don't want to burn your hand. So if you do, you might drop the flare. So that is the reason why we should avoid.
It's a handheld signal. Once you hold it here, the flame, it's quite close to your hand. So That's the reason why there should be minimum slag formation. And for safe use and safe production, it should contain chemically stable compounds of minimum toxicity. And so to generalize, our goal was to find an efficient composition that burns slowly. And this is something that that sort of contradicts itself, because the main trend that we see when we analyze pyrotechnic, the illuminating pyrotechnic compositions, is that if the burning rate goes up, then the efficiency and light intensity also goes up. But we wanted to find something different that essentially burns slow. And in our case, we wanted to find something that burns slower than, let's say, 2 millimeters per second, and to still maintain high efficiency. So before we go into details about the experiments we did, for those who are watching us that are perhaps not so familiar with the chemistry or the parameters that are associated with this kind of research, we would like to mention some of them and perhaps give a small explanation on the side. So burn rate, so this is something that in the literature is also referred to as a linear burn rate. It is measured in millimeters per second. So, well, this is generally when having a pyrotechnic column, we want to see how rapidly does the burning progress to the depth of the pellet or the column. And this is because there are two ways of, let's say, burn propagation in fireworks or pyrotechnics, which is the surface propagation, like when you have the quick match. So the surface propagation is more pronounced, and that's where you get the high, let's say, high fast fire transfer. In this case, we talk about how when the burning progresses to the depth of the pyrotechnic composition. So that is the burn rate. Now the light intensity is measured in candelas. So the measurement is being performed using a lux meter, and one important, let's say, parameter that we enter during the measurement is the distance from the flare to the lux meter or to the observer, and taking that into account, we can have the measurement done and measure the flame brightness in candelas. And then another parameter that is, let's say, that derives from the light intensity measurement is the efficiency, which you can see right here. So it's L specific, and that is defined in candelas or kilocandelas, which you will see later on. So candela seconds per gram. So this is a measure of efficiency. And well, to give an example, let's say a composition which has an efficiency of let's say 1000 candela seconds per gram, it means that 1 gram of composition, which is just like a half of teaspoon, in 1 second, it burns to produce that amount of light constantly. So is this clear enough there? What do you think?
I hope so. And I guess we'll see later in the questions if it was unclear, but I think it's fine.
Yeah, sure. We have no problem of coming back to this, and then for those who are watching, feel free to ask questions about anything that we talk about here, and hopefully we'll give you some feedback at the end, or even if there's something specific and short, perhaps during the conversation. So, and final parameter, we will not talk about this a lot. It is something. It is actually the ratio between the efficiency and the burn rate. So it was something that we used ourselves just to get an indication which composition is both bright and slow burning. So I will not go into details about this. We may come back to it later on. And now, yeah, color purity. So this is, I think, quite interesting for the fireworks people. So to have an idea how pure the pyrotechnic, the fireworks flames are. And this is also associated to the hand flare. So we have the three main elements that produce the color flame in fireworks. So strontium, barium, and copper. And we have the purity scale from 0, which is white light, and to 100%, which is a fully saturated color. So for the flames of, let's say, strontium, it's not particularly difficult to stay in the range of 80 to 90 to 100%, because strontium emission is quite strong, and it's one of the strongest in pyrotechnics. And for that reason, all the background emissions, like incandescence or impurities like sodium and potassium, they're not as pronounced, and for that reason, does not overshadow the red flame. So it's usually in that range for barium. It's in the range of around 80 to 60%. And that is, I guess, due to barium oxide continuum pair. Is that right?
I guess so, and another explanation is that barium is not as efficient at producing all of its energy, or the barium monochloride is not as efficient as strontium monochloride when it comes to producing visible light. A lot of energy is also lost outside the visible spectrum. So that might be part of the explanation too, I guess.
Yeah, true. And yeah, when you measure these kind of compositions with a spectrometer or a luximeter, you do observe that strontium flames, they're usually several times more bright than barium. This is the interesting part, that the sensitivity of human eye is exactly the opposite. So when you view the flames, then since the human eye is more sensitive to green light, then it's sort of the barium emission sort of catches up to strontium. And for that reason, in the color flame compositions, when you replace strontium nitrate with barium nitrate, you usually get a pretty similar effect. So, well, that's an interesting point here. And now copper flames and copper emission, it's lower than, let's say the color purity is lower than strontium and barium. It's usually, at least from the experiments I did, is usually in the range of 30 to 40%, and the best compositions reached 50%. With some exceptions of, let's say, small pellets, they're even of a higher purity than that. So, but we will not get too much into this. So yeah, the main chemical components used in these flares, I think fireworks people are quite familiar with: strontium nitrate, the anhydrous form, magnesium powder, and of course the particle size play an important role here. We will also say a few words about that. We used rounded magnesium powder, which is something in between spherical and let's say granular shape. So the particles are rounded, and well, I'm not so sure about how it is being manufactured. Per, do you?
I think it's a tumbling process. They have chips or grindings that they just tumble for a while to round off the sharp corners. And then you end up with a material that is not as active because you have less surface area, and that was important to make this composition really efficient.
Yeah, and I guess it's also relatively cheap in comparison to the
atomized form.
Yeah, the atomized or the spherical magnesium. Is that right?
Yes, that is very expensive, too expensive for us. And usually too expensive for fireworks too.
Yeah. Okay. So, and Then it's chlorinated rubber, perlite or porcelain. So there are several choices to be used here, and we used chlorinated rubber specifically, but other alternatives can also be used here. They're quite similar, let's say like saran or chlorinated PVC or PVC also. Then guanidinium nitrate. So this is an organic compound. It's an energetic material. So it is a nitrate. So it has the oxidizing moiety, and guanidinium, it does act as a fuel. So this material is described in several pyrotechnic books, also in Shimizu's book. And we have found it to be quite efficient in the flare compositions that we used. So we'll come back to this. And linseed oil, it was used as a binder and as a material also to protect the magnesium powder. Okay, so now we will move on to the experimental section. So for those who have questions about the materials, feel free to ask us in the comments. So we would be happy to comment if in case something isn't clear. So let's move on. Right, before the experiment. So again, this is how the hand flare looks like. And as I showed before, I have an example here. So, and in the bottom of this slide, you can see some pictures how the flare's chimney looks after the combustion. And you can see there is some slag that is being formed. And this also indicates that, let's say, not all of the combustion products leave the flare, and some of it gets deposited on the walls. So it's also something to take into account when talking about the balance of the composition and the stoichiometry and oxygen balance, and also, yeah, spark formation.
Can I just add, Dominykas, that kind of chimney effect really disturbs both experiments and the way the flare burns, because it can act like a nozzle, and it can increase the gas pressure and therefore also the burn rate. So although we didn't really see a clear connection to what causes this buildup, but it's something that we don't want to see. And the best compositions did not create much of this chimney nozzle effect. And it would be good to know how we could avoid them completely. But as I remember, Dominykas, we did not really see how to get rid of them fully.
Yeah, it's an interesting question. And as far as I remember, when we took some flares and then sort of scraped the sides of the flare, so I remember we observed that there was quite a lot of carbon there.
Yeah,
it seemed like it was a very carbonous residue, and I guess that is connected to the combustion being incomplete and the very low oxygen balance that we are dealing with here. What do you think?
Probably. I mean, it's the compositions we tried are all very fuel rich. And we tried a little to find some kind of additive to get rid of that buildup, but we didn't find it. But the best compositions, as I said, they worked nicely without this chimney.
Mm-hmm. Okay. Yeah. So now moving to perhaps a few words about the geometry. So again, this is for those who are making the compositions for fireworks and making star compositions. So what we will talk about is something that is similar to what you have in fireworks, but just to mention that even though they're similar, there are some differences that should be taken into account here. And perhaps one of them is that we are dealing with constant burning here when, let's say, the combustion surface is constant during the whole process. And in the case of fireworks, when we're talking about stars, let's say either pressed, rolled, or or cut, both of them burn in a way that the burning surface decreases. And that also is connected to the heat feedback to the composition, how much it is heated. And that also defines the burn rate. So all of these three factors, they are interconnected. And on top of that, on top of all of that, we have the wind speed, which is also a factor. So it's to say that even though these compositions worked quite well and produced brilliant red flames for the flare, it doesn't immediately mean that this kind of compositions would produce, let's say, red dahlia stars for fireworks. I mean, they would most likely have to be tuned a little bit. So, okay. So the first experiment, yeah, this is as boring as we can get. Lots of numbers, but we won't spend too much time here. This experiment was to investigate and to see how important is the chlorinated rubber, and can the compositions tolerate really large amounts of rounded magnesium powder. And as you can see, 45 to 100 microns. This is quite fine powder that we use. And of course, the rounded shape, as we mentioned before, it also played an important role because magnesium was, let's say, less reactive than the other this particle size. Still, let's say it was simply just less reactive, to make it short. And after this experiment, we took measure of the density of the compressed composition. So then the burning time of the flare. So these were the columns of, I think it was 7. Okay, I think we're back. Can you hear me?
Yeah, but
Okay.
it's like it's a bad connection or something.
Yeah, I got the impression. Should we go on?
Yeah, do that. But your voice is lost now and then, so I hope it gets better.
Okay.
Yeah. So we lost him, Per. Why don't you pick it up for a bit?
Okay. I don't know if you hear me, Dominykas, but I will try to continue for a while in your place. What was interesting about this table, the first set of experiments, was that we could use such a high amount of magnesium and still produce a good red flame, and also that we used lower and lower amounts of chlorinated rubber and still had a very good red color. I don't know if you can see in your screens, but on the last, like in experiment 13 and forward, if you look at the LSP row, you can see that the efficiencies are really high. And this is interesting because it means that in this system, chlorinated rubber acts like a flame retardant, and it's actually not that good to have. Of course, we need the chlorine, but the less we have of the chlorinated rubber, the better the composition performs.
Yeah.
Are you there, Dominykas?
Yeah, I think so. Can you guys hear me?
Yeah, now and then.
Okay.
So
yeah,
is
we'll
there
try
something more to add to this to this slide. Did you want to say something more about the certain experiment numbers or in general regarding the low amount of chlorinated rubber?
I think that is it. The only thing that I could add is that the problem with these, even though we obtain these very high efficiency numbers, the burning rate really went up, and that was something that we didn't want. So I think at this point we thought about how to compromise and how to, let's say, sustain the high efficiency and to reduce the burn rate again. And this is actually, this slide right here is the same experiment plotted in the triangle diagram. And so linseed oil, the amount of linseed oil was constant, and we changed the amount of strontium nitrate, chlorinated rubber, and magnesium. And from this picture you can see here, the composition that we further wanted to investigate was actually this one right here, which contains 14% of chlorinated rubber and 48% of magnesium. And you can see it's still on this edge of 16 kilocandela seconds per gram, which is a pretty good efficiency. And we decided to go from here and hopefully reducing the amount of chlorinated rubber even further, so that the compositions can also push towards this efficient area right here. Okay, I think that is it on let's say on this slide. And so then we ended up having the composition which contains let's say strontium nitrate 34%, rounded magnesium powder 48%, chlorinated rubber 9%. So originally it's 14%, as I just mentioned, but now we split that in two, and we use 9% of chlorinated rubber, and then we use 5% of the additive. And at this point we tried different additives, which you can see on the right hand side. And of course already people might ask, okay, why we chose these additives. Some of them were chosen based on the literature, and some of them I guess were just intuition, and some of them I guess was just shot in the dark, right, Per?
Shot from the hip. Well, it was all of them we were interested in them. I had them in my chemical cabinet for a reason. They had been efficient and useful in other experiments, and we wanted to evaluate is there some kind of trend when we add an additive, so we can kind of predict what kind of additive will be more efficient than another.
Yeah, exactly. And some of them that we tried were really some of the things that we found on the shelf, but there's of course a reason for that. And one of the main reasons is that some of these materials are gas generating materials, and 2-cyanoguanidine melamine, they both have nitrogen. Azodicarbonamide, it is used in, I guess, in conditory as a foaming agent. Is that right?
Yeah.
Yeah. Then we have some of the materials are pyrotechnic fuels or additives. So like calcium resonate, shellac is a good fuel we wanted to see, and then strontium oxalate. It's something that also adds some additional strontium, and the rest is just decomposes into carbon monoxide and carbon dioxide. And I think that lactose was the point when the things got interesting, and because when we tried lactose, it was something counterintuitive. We didn't expect anything much from lactose, but in fact that worked out pretty well. Is that right?
Yeah, better than as you say, better than we thought. Yeah.
Yeah, and this is generally replaces chlorinated rubber, and it was quite efficient. Of course, now in the table we have a lot of numbers, but if we take a look at lactose, the burn rate, it's pretty similar to the standard. And let's say the LSP and the actual light intensity of 25 kilocandela, that is quite good for this type of flare. So we knew that something was up, and we wanted to take it even further. And so just to go through the additives, dextrin is pretty similar to lactose, phenolic resin, the common fuel. Lignin sulfonate, this compound has some calcium and some sodium. So again, there are additional emissions that are added. And yeah. Then 5-AT is 5-aminotetrazole. So this is a compound with a high nitrogen content. I think it's around 80%. Then it's urea, guanidinium nitrate, and hexamine and sulfur. So yeah, after comparing, let's say, burning the flares using these additives, we have, let's say, looked at the results in, because they were quite random, and we wanted to spot some trends. And some trends you can see in the next slide right here. And I guess the one that really depicts it well, it is with some help that we got from one of our colleagues in Germany, is when he suggested us to plot, let's say, the efficiency against oxygen balance. And at this point, we noticed that there is a trend that the lower the oxygen, because these compositions are very fuel rich, meaning oxygen deficient. So in this system, we saw that really materials who have some oxygen and are, let's say, gas generating materials like guanidinium nitrate, it was really a great additive, because it also reduced the oxygen balance, which is already quite low, and helped to produce more light. So, and just to see in this graph, some dots are full, some of them are, let's say, or hollow, or how can you call
empty.
it? Yeah,
empty or white. Yeah.
Yeah. So we mark them white because they actually add some, let's say, some additional species to the flame, which are additional emitters, or let's say chlorinated rubber. So it's extra chlorine for the strontium chloride emission. And so looking at the black dots alone, we see that it's a pretty clear trend that with, let's say, decreasing oxygen balance, the efficiency really goes up. And this sort of led to the conclusion that, okay, guanidinium nitrate, in this particular system, when we have so much magnesium powder in the composition, it really works out. And yeah, and same for some other compounds. So yeah.
I can just add that, as you said, we had this composition that was good but burned too quick, and we wanted to add a secondary fuel just to make it burn a little slower. And it was really contra-intuitive that the fuels that are very good in ordinary fireworks compositions like shellac and phenolic resin, they didn't work at all as an additive to an already magnesium-rich composition. But we also had high hopes for the 5-AT, but that is a very expensive compound. So it was very interesting that guanidinium nitrate, that is not as expensive, and also some of the other simpler chemicals like lactose, melamine, that they were so good. So I mean, maybe some people, they don't have guanidinium nitrate, but maybe you can use something else if you have a look in this graph. And that is really interesting, and the way the additives act to expand the flame, maybe that is something you will come back to in later, Dominykas. So would you like to say something about that now?
You mean about the flame expansion?
Yeah, I mean, why? What happens when we add? Why do we see an positive effect from guanidinium nitrate?
Yeah, I do remember that even during the experiments we talked a lot about the, let's say, the flame expansion, but at this point I'm really looking at let's say the values of the oxygen balance and at this trend right here, and I guess it really is associated to the lower oxygen balance, and I'm sorry, the more positive oxygen balance, which is, let's say, if we move from this side of the graph to that side, when it really helps combustion, then it becomes, the composition becomes more efficient, and because mainly if we're talking about the gases like water vapor, it is being consumed by gaseous magnesium, and nitrogen. Okay, so nitrogen is something that hopefully stays and expands the flame. So yeah. I guess there is some flame expansion from nitrogen.
Yeah. What I was pointing out was that different fuels combust into different kinds of gases, and both carbon monoxide and carbon dioxide can react with an excess of magnesium in the flame, as water vapor also can. And I think that is part of the explanation, that if you have something that only contributes with nitrogen, it will not be as efficient as if you have some carbon monoxide or dioxide too.
Right. Yeah. So we have some ideas about, and it's an ongoing discussion about, let's say, these additives and the way they add to the color flame. But I guess as we can go on, and perhaps we'll come back to this.
Yeah.
If there are some questions.
Dominykas, I have a question that just came in from Matt Noob, and the question is the lignin, I can't say this, lignin sulfonate, would that affect the flame color, shifting it closer to the more sensitive areas of the visible spectrum?
Is lignin sulfonate shifting the spectrum towards the more sensitive areas of the visible spectrum?
Yes.
Well, it makes the red color less pure because it contains some sodium and calcium. It's a byproduct from the paper industry. It's a brown powder that burns as well as phenolic resin, and it's a very interesting and cheap fuel for pyrotechnics. But it's not as good if you want a pure color. But as I said, it's a very reactive fuel, and the reason it's so high in this diagram is because you get some emission from the calcium and sodium, and therefore more light, but it affects the flame. And I don't think we could use it for the red hand flares, because the flame gets orange.
Yeah, I think that's a good answer, and I think if the question is how much does the flame color purity, how much does it get reduced because there are additional emitters that enter the flame. So at the moment, I do not remember the exact numbers, but I guess there was some reduction. It wasn't that strong. It's definitely not like it's turning orange or yellow, but maybe there was
it's definitely a fuel that we could continue experiments with, because it's almost for free, and it burns well.
Yeah, it works quite well, and the problem for us was that it was burning rather fast. That was one of the problems that was associated. But let's say for firework compositions, sure, I think it would be interesting to try it out in this particular magnesium-rich system to see how it performs there. Because again, the red color flames, the purity is very high of strontium flames, so we can give up some color purity for, let's say, brightness, for example. I think that's possible. So anything else, Per? Should we go on?
We can go on.
Okay. Right, and now the third and the final experiment. So since we noticed that guanidinium nitrate is really performing quite well in the system, and that is indeed an energetic material that, let's say, that helps combustion. So we sort of had the idea that compositions can tolerate higher percentages of guanidinium nitrate. And indeed, that was the case. We did this experiment to see how well the flares behave when the guanidinium nitrate content is, let's say, from 10 to 25%. And again, even more lowering the amount of chlorinated rubber in this case. And I think this is really an interesting, one of the interesting parts of this experiment, that if we take a look at the amount of chlorinated rubber and we look at the flame color purity, it's really, really high. Some cases it is lower, but that is due to, this is associated with the spark formation, but some numbers are very high and the amount of chlorinated rubber is very low. So this was very interesting to see. And again, the amount of magnesium is high. It's from 40 to 50%. And the amount of linseed oil is lowered just a little bit, just to get perhaps even more efficiency, from 4 to 3%. And let's see, when we looked at these numbers, we were really happy that we finally got these low burn rates. And it was lower than 2 millimeters per second. That's something that we were hoping for. And also the LSP values, the efficiency values of, let's say, 22 and 20 kilocandela seconds per gram. These are like record numbers that we, because we didn't find anything in the literature that, let's say, passes, let's say, 22% with such a low burn rate and with high color purity. So the compositions were quite efficient. Yeah, very efficient. And just an interesting mention here that one of the parameters that is quite hard to define, but something that we always observed visually, was the spark formation or the slag. So let's say when we have the flare, so we always, I mean, during the video, we observed that some flares, they produce a flame which is consistent, and all of the combustion products just leave the flame. But in some cases, we have realized that we have noticed that some of the, let's say, glowing droplets or sparks, they actually start sort of shooting to the sides, or even fall down, let's say, fall from the flare. So, and the number here for spark formation, where we have written 0, so that means that there are no sparks in slag form. Number 1 means that there are just some sparks, but very small ones that erupt and jump to the sides. And number 2 is when there are really significant amount of glowing slag that starts falling to the sides here. So that is something unwanted. But interestingly, in the case when we have, let's say, 0 amount of sparks or slag, let's say the purity, even though that's not a problem, but the purity is lower. And when we have, let's say, on the other side here, when we have spark and slag formation, which is unwanted, the purity is actually very high. So we had discussion about this as well, and it's an interesting phenomenon that we think that this has to do with the amount of, let's say, solid particles in the flame. So yeah, the amount of solid particles in the flame, let's say it's the same, but what matters is how fine they are and how strong can they glow in the flame. And it seems that very small particles, and when you have a lot of them, the gray body radiation that come from molten particles or solids, it's very strong and very pronounced. And when you have, let's say, bigger particles, in that case, the emission is not so pronounced, and the strontium emission is, in that case, stronger. So, yeah, just a few remarks on how the flame color purity is connected here to the spark formation.
Dom, Steve here, second. I was wondering if we could get some comments from Joel or Dr. Winokur at this moment, if they have something on their mind. And while we're doing that, if you would check your chat box there's a couple questions you might want to address.
Yeah, okay, sure.
So Joel or Bob, do you have anything you could say at this moment in time?
This is Winokur. All I can say is that I'm very impressed with the approach.
Thank you.
Thank you.
This is the way pyrotechnic studies should be done. There's no conservativeness in terms of you're not afraid to try things that are kind of counterintuitive, and sometimes you discover they work. And at the same time, you're making a logical course of actions on trying things that you think should work. And I think both things are important to do.
Very good. Joel, do you have anything to add to that?
Well, yes, a number of things have occurred to me. I think the top one right now is there some particular reason that you didn't go with polyvinyl chloride or CPVC, which are featured prominently in the NATO formulations in BIOS in Lancaster and in Ellern and so forth, because the conventional wisdom seems to be that polyvinyl chloride is less reactive in storage and it can tolerate higher temperature flames. So I just wondered what led your decision to stick with chlorinated rubber. And then the other quick question is, what is it about the 5AT that is detrimental or did not meet your expectations?
Well, I can answer the first question, and the main reason is that we have always used chlorinated rubber in our compositions, and it was kind of the first goal to continue using that in all these sets of experiments, because the aim was to develop a new hand flare composition. But in my opinion, when dealing with high magnesium content compositions, PVC is not as good, simply. And it's also usually very powdery and dusty to handle, and the chlorinated rubber are usually less dusty, so it's a practical thing also. But I'm sure that we could reach similar, maybe better results with PVC or chlorinated PVC or even saran resin if we had it. But the chlorinated rubber is available and it's cheap, and we have tons on it here in the factory. So that is the main reason, actually. And maybe you, Dominykas, can answer the second question regarding 5AT, because I'm not that familiar with it, with that composition or that ingredient.
Right. Yeah, just to add to Per's comment about, let's say, and to answer Joel's question about different chlorine sources in this case. Sure, it would be interesting to try it out. I know we didn't try, again, for the reasons that Per mentioned, that it was good material, it worked out, and we didn't even have a reason. We didn't know a reason why to try the different ones. And okay, maybe some parameters like for storage or for handling, maybe some of them are better, or maybe some of them have a better price than the other. But from the chemistry and from the point of color flame production, we didn't spot anything.
There's also some areas. I just wanted to mention, Dom, sorry, that there are some areas that we can't mention. It's a secret that is connected to chlorinated rubber, and we need it, actually.
Okay. Yeah, I don't know this, but it's also
connected to binding the composition. in a certain way.
Okay. Yeah, sure. So it's it also works. They work as a binder, but also let's say from the color flame production point of view, I have heard some thoughts that materials like PVC, when you look at the thermodynamic, let's say the decomposition of PVC, and some say that, I don't really remember now what was the case, but PVC has certain benefit over other chlorine sources that I think it's the case that either it is very, I think there's a kinetic parameter that is associated with PVC, but I cannot.
It decomposes more. It decomposes more easy. You
Right.
get more. Usually, you get more slag from a chlorinated rubber composition. But in these compositions, when we have such a high amount of magnesium, we don't see that. But you will do if you have an ordinary fireworks composition that works at a lower temperature.
Okay.
So well. But Joel had a question regarding 5AT, and I forgot what it was. Can you repeat that, please?
Yeah.
I just wondered how you found it to be. It didn't meet your expectations. It has a very high nitrogen content, which in some quarters is considered to be highly, beneficial for reducing smoke, for example. There's quite a bit of information that's been published about that, and I just wondered how did it diminish the flame color? Did it just reduce the flame size? Or decrease the burn rate? What was the major detriment compared to the guanidinium nitrate, for example?
I can answer from my practical point of view. It is simply so expensive that you don't get the bang for the buck needed. Okay. That is the main reason. But it is good. It's a great additive, but it's too expensive.
Yeah.
I have been told that the 5AT fails the German test for high explosives, that it has to be shipped as a high explosive. I don't know if that's true in your corner of the world, but I've told that.
Okay, I don't know about that. Do you know anything about that, Dominykas?
No, I don't know anything about that either. But PVC, I mean, in some of the more recent experiments that I did, it's PVC, sorry, not PVC, but 5AT is also like a fire retardant. And if you, let's say, combine that with ammonium perchlorate, it's quite hard to burn it. You have to have some additional additives to, let's say, to help combustion. But again, I don't know if I fully understood your question, but what I can mention again is that we're talking here about a very particular system, and here we tried only 5% of a certain additive, and when we compared them, it did seem that it was, it was good. We're not saying that, let's say if we come back just one slide back here, so it wasn't that at all. It was somewhere close to guanidinium nitrate, and well, it's just one step away from it. But again, it is. It was, in this case, it is. It's the most expensive of all of these that are used, and the performance. Let's say in this case, when we look at the oxygen balance, guanidinium nitrate is even better. And when we look at, let's say, the smoke production, well, I guess we didn't pay that attention when we tried, let's say, the additives. But then again, it's only 5%, so it's a small amount. So I think it's pretty hard to distinguish or to have something noticeable. So maybe a larger amount should be tried. And we do know that 5AT and let's say hexamine have been recently investigated in more detail, and there are some publications out there about both 5AT and hexamine. So they do have potential, but let's say in this particular experiment, and from the results that we have and the system we investigated, well, they stand where they stand, so to say.
Can I just ask Joel again? What our good friend Bertolt Schwartz he would like you to repeat your remark about 5AT not meeting Germans' explosives. What was it? He lost, and also I didn't really get. Is it not approved in Germany? You mean, or was it something else?
Well, the specific reference was that I was working on a project with a person, an analytical chemist, who's no longer living, from the Federal Department of Transportation, and I had mentioned that there was use of 5AT in some literature for smoke reduction. And he was interested in transportation issues. That's what we were working on. He said, well, it's a difficult molecule to make. For one thing, it's hard to attach those atoms together in the way that you want them. It's a difficult process, and it fails the German test for a high explosive. And I believe when ignited under confinement or something, conflagration to detonation progression, but I don't know any more about it than that. That was just a comment that was made without any, no specific references provided.
Okay, but well, I don't know anything about that. We only know that there has been lots and lots of experiments using it, and especially in the area of green pyrotechnics. Some people thought it would be the savior, but well, maybe it is, but we also see that we don't need it, at least not in this case, because guanidinium nitrate is like the poor man's 5AT. Dominykas, Berthold Schwartz also wonders if you could again briefly explain the oxygen balance, the omega percent, how it was determined.
Right. So, yeah, that's a good question. It's something that I didn't mention. So, the omega, the oxygen balance is, we're talking about the oxygen balance for the whole composition. Yes. So it's not, let's say, each of these compounds alone, but we're talking about well, 34% of strontium nitrate, 48% magnesium, 9% chlorinated rubber, linseed, and then 5% of each of these. So for that reason, it's in this area of very low oxygen balance. And just to add, I mean, oxygen balance, what we're talking about, it defines how oxygen deficient composition is. And just to give an example, if we're talking about, let's say, the flare composition with 5% of shellac right here, so it means that 1 gram of this pyrotechnic composition burns and still needs extra 0.5 grams of oxygen to completely burn. So if the oxygen balance is 0, then the combustion is complete. And in this case, let's say in the negative scale, so additional oxygen is needed, which, by the way, is an important, interesting point that in the case of flare, when we have it here, so it's like a primary combustion that takes place inside the flare's body. And then there's the secondary combustion when the air oxygen rushes in and oxidizes magnesium and let's say hydrogen, which are there. So yeah, I hope this is more clear now.
Yeah, and we might also mention that the reason we say guanidinium nitrate and not guanidine nitrate is there's an analogy. If you don't say ammonia nitrate, you say ammonium nitrate. So yeah, we have been told by someone in Germany who knows everything that the correct name is guanidinium nitrate. So
yeah, exactly. So it's essentially the same material, and we use the abbreviation GN for it. And yeah, I think we can go on from this point. Yeah. I haven't looked in the comments. Should I take a look there?
Oh, I'm checking it. So I think you can
Per's
go on
watching
now.
that, and that's good. And just to let you guys know, you know, we've gone, we're past the hour, but we haven't been cut off, so you're good to go. But you know, go ahead and pick up the seminar where you're at, and we'll see where this goes. Thank you.
Okay, perfect. So, and the final experiment, I think we discussed most of the points that we wanted here. So again, for mention, for those who are just joining us, so we have looked into, let's say, the classical compositions of strontium nitrate, magnesium, and chlorinated rubber. And we noticed that by reducing the amount of chlorinated rubber and adding guanidinium nitrate in this particular system, we have really achieved what we wanted, is that we have achieved low burning rates of, let's say, 1.8, 1.5 millimeters per second. And still the light output was extremely high, which was, let's say, you can see the light intensity here. It's, let's say, 18, 25 in some cases, sometimes even 30,000 candelas from a flare which is 21 millimeters in diameter. So this is quite large. And hand in hand to that goes the flame color purity, which should be also, yeah, when doing these experiments, we keep track on it as well, and the slag formation. So there are 10 compositions. One are better than the other in one aspect, the other is better in the other, but the general trend, I think, is quite visible here. So I think we can move on. And right, since we measured the emission spectra of these compositions, so for those who aren't so familiar, so here we have the, let's say, the scale of wavelength and the intensity in arbitrary units. So the visible spectrum is from 400 to 700, and near 700 we have the red, then the orange, yellow, green is somewhere here in the middle of 555 nanometers, and then here we have the blue section. So you can see in the blue and the green sections there's fairly any emissions present, but in the red emission we have the emissions of strontium monohydroxide and monochloride, which accounts for the red flame production. And really here, what we want to show is really the battle between the strontium hydroxide and monochloride versus the background radiation, which you can see that stretches from the infrared and goes all the way to here, and then also in the visible spectrum. So in case, and here we see how it is connected to, let's say, the flame color purity. If the background radiation increases, then the color purity goes down. For example, here it's 83%. This is the top spectrum. And the spectrum with least incandescence emission, or the gray body radiation, is the most, produces the most pure red flame. So I think there's it is just that at this point, and it also helps us to, let's say, investigate these compositions, and especially when we're looking for a good color purity, we want certain emissions to be present and certain emissions to go away, so to say. So, right, and finally, so since we ended up having compositions with really low percentages of chlorinated rubber, we wanted to take it one step further and to see if we can completely avoid it, and that wasn't too difficult. We got the composition that contains a little bit extra, so it's the composition C here, or 44, so which contains essentially the same amount of strontium nitrate and magnesium, and it has a little bit more guanidinium nitrate, and magnesium stearate here was used. I guess we used it to compact the composition better.
We had some flow problems. We wanted it to flow through funnels better, and adding magnesium stearate helped that a little, and it also made the composition burn somewhat slower without sacrificing too much light. So it was a good additive in a small, when you're using just a small amount of it.
Right. So composition is pretty simple, and let's say the light output and the efficiency was 16.2 kilocandela seconds per gram, which is good, which is in the range of the other compositions. So not to say that we lost the 6% and we lost the strontium chloride emission and we lost the red flame. And at this point, it was mainly the emission spectrum contained of strontium monohydroxide, which produces rather an orange-red flame color. So and also the purity is just a little bit lower. And I would have to look up and see if that was because of incandescence, which I would assume. But perhaps there was, yeah, it should be incandescence. Yeah, I think it should.
You mean the explanation for the low color purity?
Right, right.
Well, I guess you can never reach the same purity without the monochloride, but it was almost good enough. But I would not count on a red flare being based on the strontium monohydroxide emission only to be approved for marine use. We could try it, but I think we need some chlorine.
Yeah, exactly.
But it was a really interesting experiment to see that it was clearly red, and especially at a distance, I'm not sure you would see a difference.
Yeah, yeah, it was interesting, and just a remark from the chemical point of view is that when you have some chlorine in the composition, so part of that goes and contributes to the let's say color flame production, so strontium chloride formation. But let's say the other part of it can actually help to vaporize the metal, which is magnesium, or in case the aluminum is present. So just to say that, well, we would have to check the thermodynamic calculations for this, but it might also be the case that if we have at least some chlorine, then it also helps to vaporize magnesium, which reduces incandescence and or the gray body radiation and increases the flame color purity. So that is also connected, so to say. Right. Okay. And now finally, since we went through so many technical details, we would like to show 2 videos. First of all, we will see again the composition which we showed in the very beginning. So it is a flare composition with guanidinium nitrate. So again, we'll watch the video, and from the beginning, after the ignition, you will see the flame erupting. And yeah, let's just go ahead and take a look. Ignition. Right. So as we can see that no large amounts of slag are not falling down from the sides of the flare, and the burn is quite consistent. So again, the composition is really balanced for, let's say, this type of a flare for the metal casing, and it's optimized for this system. But we were quite happy to see this kind of combustion, and it's extremely bright. The camera, of course, doesn't show that, but holding this in the hand, you can barely look at it.
You shouldn't.
Yeah, exactly. So, and the next one, and this is something different that we did, was that we just from the interest point of view, we replaced strontium nitrate with barium nitrate, just boldly dumping it there, and just to see what happens. So we will see that just in a second, and we can already get some clue that the dominant wavelength is shifted towards the green region, and the color purity is somewhat lower. So let's take a look at that one. Right. So that's definitely not red.
No.
We
But
have a green
the
flame.
interesting thing is that, but we have already discussed that barium is, when you do measurements, you usually get kind of low readings, but looking at illumination with your unaided eye, it looks better than what the measurements tell you, because our eye is more sensitive to green light, and that really helps. And I guess that is the reason why it's not too difficult to balance red and green color in fireworks.
Yeah, exactly.
But we can
So
never reach the same light intensity from a green hand flare as we can with red, with one that is based on strontium nitrate.
yeah. Okay. So I think we're about to wrap it up, and just maybe to mention some conclusions, and what we learned from this is that, yeah, certain oxygen and nitrogen rich additives were noted for their ability to increase the specific luminosity, or the specific luminous intensity. Guanidinium nitrate showed the best performance as an additive in this particular system, with high magnesium content and very low amount of strontium nitrate, which is in the range of 30%, which is something exotic or very specific for this kind of compositions. So while maintaining the low burn rate, it produced around 40% higher efficiency and 60% higher light intensity in comparison with the similar guanidinium nitrate free composition. And again, the small amount of chlorinated chlorine donor was also a specific feature of the compositions that we investigated, and such a small percentage, like 4 to 6%, was efficient. So we were, of course, surprised and very, very happy with that. And finally, we, since the compositions did tolerate such a small amount of chlorinated rubber, so the magnesium-rich chlorine-free composition was investigated with the help of guanidinium nitrate, which burned, let's say, in the similar light intensity, but with just slightly reduced color purity in the range of 80%. So I think that is all that we wanted to present today, and now we can move to the questions.
Right. So yeah. So Bob or Joel, if you could take that.
Well, the one question that came up as I listened to your talk was, did you ever consider using magnesium in these kinds of experiments, and what would the aluminum damage the color purity?
Well,
Right.
we thought that it would be a problem, and also there could be a problem with the raised friction sensitivity in the production. So it was really never an option. And I can't remember, Dom, did we ever try it? Because of course we have magnesium, but I can't remember if we tried it during your work.
Right. I looked at the compositions once more, but we didn't try magnesium. However, we did try a combination of atomized aluminum, again, to have the low burn rate, and combination of that with magnesium. So we tried a combination of, I think it was around 40% of magnesium and then 8% of aluminum. So to my memory, that was, I think it was quite similar,
Yeah.
but it wasn't like it had a significant effect either on light intensity or anything else.
But
So,
my guess is that magnesium would not work, because I guess we would have problems with the burn rate and also with the color purity, I'm sure, since we need so much of the metal to reach these high light intensities.
Yeah, I also think that magnesium would really add a lot of reactivity since, again, looking at the particle size of magnesium.
And the particle shape.
I never even heard of atomized magnesium. Is that even available?
Maybe, but not commercially usually. But
yeah, exactly.
as you say, the particle shape, it's many sharp corners, and it's a very reactive fuel, and we need a high temperature fuel that is not too reactive to reach these slow burn rates.
Yeah. So I think that's the answer regarding magnesium, that we simply didn't use it because of the high reactivity and yeah, also for the fact that it would be more friction sensitive. The composition would become more friction sensitive in this case.
Thank you. That was a useful answer.
Joel, do you have anything to add?
Well, I can fill in the background on these metals if we have time for that in about 90 seconds. Is that all right?
Sure.
So the thing with atomized metals is that aluminum ignites at a much higher temperature than its melting point, so it can be blown into natural atmosphere, which is not very expensive to do. In order to make spherical atomized aluminum, they have to blow it into nitrogen where it becomes ellipsoidal, or they have to, for spherical, they have to blow it into argon, which is very expensive. For magnesium, if they want ellipsoidal atomized magnesium, they can use nitrogen, which is not so expensive. If they want spherical atomized magnesium, which is used in some rocket propellants and things like that, they have to blow it into argon, which is very expensive, and they recover that and decompress it. The problem with magnesium is it's reactive enough, and it has a higher melting point, that it has to be blown into argon in order to make an atomized magnesium. At that point, the expense is so high that there's no point in it, because we'll go to magnesium at that point. There's also a 70-30 magnesium, 70 magnesium, 30 aluminum that is a military flare grade, and I forget what they call that. It's a Joint Army Navy number, but there is a flare grade of magnesium that is used, but the ratio is 70 magnesium to the aluminum, and that is a comminuted type powder. It's only about a 50 mesh in production, so there is some precedent for that. What type of flare is used in I don't know.
Actually, for me, it's really hard to hear Joel at the moment.
Yeah, but I think, I mean, I heard most of it, and it's true, and it explains the difficulty producing spherical magnesium. I did not catch if you, Joel, know about someone ever produced atomized magnesium.
Not commercially that I know of. I just know it's been explained to me by the magnesium representatives from several companies that is the reason they don't produce it. I'm sure someone has tried it, in the past, but the expense is so high that there's no advantage at that point, so they just stick with it.
Okay. Yeah. Perhaps if we talk about magnesium, we can also have, mention that there has been an interesting system analyzed by Dr. Arno Hakma, and he investigated similar compositions that contain not magnesium, but it contains a combination of zirconium and aluminum, and there is an interesting chemical mechanism that is associated with that kind of combination, which is, well, I guess not that practical for firework people, but just from a fundamental point of view, it was quite interesting to see that something like that is possible, and you can obtain pretty high color purities with that, and a lot of light. So
was that connected to the combination of the slag products having a low boiling point or something, so you get a clear flame without as much incandescence as you would have if you used zirconium or aluminum alone?
Yeah, exactly. That's the case. So there is a certain ratio between zirconium and aluminum that is efficient. And the same principle is also, I think, adapted for magnesium, that when you use this in color flame compositions, well, I have to look this up. It's about these eutectic points of the oxide, of the oxides. But it might also be the case that magnesium, like why magnesium helps to produce pretty nice, brilliant colors, is that the oxide of both metals create an eutectic mixture, which has a lower melting and boiling point than each of them separately. So.
Yeah.
All right, very good. Any more questions or comments? Anybody out there?
Well, I'll defer to the other participants if there's anybody else.
Go ahead.
Well, there's just one small thing that I've puzzled out over the years. There are some formulations from Hit Fireworks in Seattle in years gone by. There's at least one from Brock. And I have noticed that there's some that combine magnesium and aluminum powders separately. And I always wondered, well, is that to make a trailing effect, or is that part of the illumination? Because they're called illumination stars. And I eventually came to the conclusion that the magnesium formula simply burned too fast with the light output, and they actually used the aluminum as a burn rate retardant. And that was a way of moderating the burn rate so that they could get a bright star that lasted longer. So that's not, that doesn't mean much in this conversation, but it is something that appears to have been done at one time. And I just thought of that because of the mention of the zirconium with aluminum. So that might be some of this.
Yeah, that was interesting to hear. I never saw a use of aluminum like that. It's interesting. So maybe it's something to try out.
There's one in Brock based on barium nitrate, and it's barium nitrate, aluminum, magnesium, and rosin. And it's somewhat greenish, but when made that way, it's very bright, but it doesn't burn too fast.
Good. Good. All right. So sounds good. Let me take this over here and share that. So I wanted to thank all our panelists today for being here. Dominykas, thank you so much for putting this together. Per, Alenfelt.
Yeah, my pleasure.
Joel, Dr. Winokur. We're going to try to continue this series over the, well, probably next couple of months to see how long it goes. That we have more people lined up. Next week, we have Kurt Medlin will be joining us doing one of his seminars on the wonderful world of wing tourbillons. Is something he's done at PGI and Western Winter Blast in the past. And we'll put some together. Bob Winokur, we'll have something from you pretty soon, right?
I hope so.
Very good. Okay. And again, thank you very much. I'd like to thank my technical staff, Joel Wright, who's been administering this, and really appreciate the support from the Fireworks Foundation, the Western Pyrotechnic Association, and also the PGI. And hopefully we'll all be able to get together in person again someday. In the meantime, come check us out again next Saturday at this time, and we'll move on from there. So thank you very much. And Joe, you can go ahead and turn us off. Thank you.
Thank you. Bye-bye.
Thank you. Bye. Okay.
And I just would like to say that it was an honor to have Bob and Joel here listening to us. That was really nice. I read both of their publications way back when, so that was fun.
Yeah, Bob, you're still on, right?
Yeah, I'm on.
Yeah, I also wanted to mention the same. I'm honored to be here and really glad that that we were given this opportunity. So we appreciate that. That was interesting.
Yeah, it went pretty well. I was watching the stream separately, and it went well, pretty well. Also, hey, Brooke, are you still on?
I am. Can you hear me?
So yeah, so what you didn't know, guys, was that Brooke, who is also one of our seminar assistants, has been lurking in the background watching this.
How are y'all? That was
And
fantastic. I really enjoyed it. Thank you, thank you, thank you. That was wonderful.
yeah, and we're gonna meet here in a bit and talk about what went well, what didn't, and so on, and refine the process. But one thing that I really enjoyed was that pair, how you looked at the chat window there and was able to bring those questions forward. And
Okay, yeah. I was afraid to open it first, but then I realized I was supposed to.
Yeah.
Oh no, that worked perfect. That was great because then I didn't have to interject, and guys, because I really didn't want to be in the conversation, but mostly get steer it. So that's something that we can look at in the future, and then also we will look at. I wasn't able to watch the in the Facebook stream. I wasn't able to watch the comments, at least because I had that running in my iPad here separately. But Joe was, and so Joe was pasting those questions in as they came in. But Brooke, this is something we're going to want to integrate into the chat somehow. I mean, we could open this up to just Facebook. The numbers, just so you guys know, we were up to about 29 viewers at one point. We were probably average 23, 24, and then towards the end it dwindled down to 17, 18.
Okay.
Okay.
So, and that's what I saw on the Facebook numbers, and those are, and that was the only meter that we had on that. So, I think certainly there were some people that were hardcore who really were interested in the material and stayed with us the whole time. So we'll be hearing, I guess from them. Obviously, what Roger Webb was paying attention the whole time,
Yeah.
and this guy Noob, whatever there were some people that really got something out of it. So that's quite useful. I recognize that I need to run another email blast for publicity the day before.
Yeah, the day of promotion.
Yeah, and that's kind of hard to do, but I have to back it up a little bit because it was sent out in 6 different places.
Well, we just need to have another draft written up and then paste it in and mail it.
Yeah. Yeah, so we'll learn about that. Yeah, so we'll figure that out. So the publicity is a little tricky, and part of that is that 3 of the email lists that we use come out in digest form, and that comes out at 9 a.m. at least my time, and that would have been a little too late if they were to see it first thing Saturday morning. The seminar had already been up and running.
What's the latest we can mail it out? Like, could we do it the night before? Is it just have to be before midnight?
Well, it would have to be. We would have to send it out Thursday night, so that it would make the Friday morning digest. And then people would have it in their Friday, because I think what has happened is that we got great feedback early on, but I believe what happens is that the message drops down in everybody's list, and then they can't find it later.
Yeah,
I think that's the primary problem. So so by putting it back in their face the day before, we'll probably do a lot better.
So was the recording successful?
Yeah. If you go to the easy thing to do is go to the YouTube link. I'm sorry, you're right. The Facebook. This is why we have you, Joe. Yeah, if you go to the Facebook page, the WPA Facebook page, and then go to on the left where it says videos. Then it'll get you there, and or you can just click on the link that we provided to get to the thing, and that'll get you directly there. And then you'll see that it's been cataloged probably already. I didn't look yet. Joe? Do you see if it's there yet?
I'm sorry. The link, it's on the website. Yeah.
Yeah. Go back and see.
Go to the westernpyro.org, whatever.
No, the WPA, not the. Yeah, it's a different. We have 2 different ones, and so.
So how did it go in general? I'm notorious for speaking in a very monotonic way, and that it gets boring, and it's kind of hard to do that and also think at the same time, you know. So, but how was it?
I thought it was fine because, I mean, you are the scientist and, you know, and
Yeah.
stuff there. The only real issue was that your audio went out a little bit there. And
Right.
so, but luckily Per was able to come in and cover for you during that period. So
Yeah, that's great. And I don't know what happened. I would assume that maybe some disturbance with the connection on my phone, because that is where the audio is being recorded. And I noticed that on the phone for a moment the screen went black and something happened, but I'm happy that it, you know, came back on. So.
Yeah, I didn't notice if it was the video and audio. Did anybody else notice?
I did not. I wasn't able to.
I did. I noticed that the audio did go out and it sounded kind of robotic and then it just stopped. But other than that, like, you were very clear and precise. And so it was easy to be able to hear what you were saying, if that makes sense.
Okay.
It was
Well,
clear.
that's of course good. Yeah, I tried to make it as clear as possible. Yeah.
Yeah, and then
I would like to say also that this presentation we try to make it as available as possible for the fireworks community, because this is not really what you might talk about every day. It's technical, you know,
Yeah.
and a little outside. But I think it's there are bits and pieces that you can learn and use. And as I said, there are some things we cannot talk about. Because we're going to use something related to this very soon in a product. I think that I already might have been saying too much, but anyway, I think it's great that we had the chance to present this to the fireworks community, and we'll just see. I guess that many people think that, oh, this was, you know, too technical or too uninteresting. I don't know, but a few people, I'm sure, thought it was interesting.
yeah,
Sure. It was very specific, and yeah, I'm glad, Per, that you joined. That was really cool having you on board. On
Thank
this.
you.
Yeah, I have a sort of a theory about, you know, these kinds of seminars, because I've been producing seminars for many years, and often I'll put a lot of effort into putting a seminar together, getting a presenter who you know, is very brainy and knows a lot about a subject, and then I'll come into the seminar room and then there's only like 6 or 7 people in the room, you know, to watch it, and I'm going, oh crap, you know. But the important thing is that when I look in the room and see who actually came to watch the seminar, and realize that it's the Bob Winokurs, it's the Joel Baechles, it's the, you know, the Tom Ravenclaws, this kind of thing. When you look at the caliber of the people who watch that, and you realize that they're taking in this really good information, and they already have a huge amount of information in their head already. They take a couple pieces and stick it together, and as a result of that, the art form grows. And that's the important part about it. Is it's not so important that we reach, you know, 1,000 people. It's important that it gets in the right hands.
Couldn't agree more.
Yeah, I agree as well. And as Rutger Webb once said, that we're the dying breed. Let's say the pyrotechnicians are the pyrotechnics. I mean, it seems like, and when you look at the numbers at the PGI, that's the youth. I mean, the average number of people, it's actually, what is it, like 50 something, 55, 57, the average age of people. Yeah. So I fully agree that we have to, it's first of all very important to share among each other, and to share the knowledge there, and go from there simply.
Mm-hmm. Yeah, so very good. So so Dom, well, I got you here. Could we talk you into doing the blue strobe one here in a few, you know, down the line a little bit?
Yeah, okay, I'll think about this.
Please do.
At the moment, I don't see a reason why not, but I have to look at this. Yeah.
Yeah, the kind of a thing. And now that we have because now that we have the process, working, and of course we'll refine it a little bit more. And then again, I mentioned that the getting the promotional out is something I got to work on for sure. But the mechanics are working quite well. And Joe's done a fabulous job here today of administrating this. So yeah, we can just keep going on that stuff. So yeah, next week we have Kurt and his seminar on tourbillons is far more pedestrian, and he'll probably have a larger audience, just primarily because that's a less brainy thing to digest, and that kind of a thing. And then we'll work on I got to work on things for further down the line. So anyway, great. Well, thank you, everybody. This has been fabulous. I mean, the fact that I'm looking at you in Lithuania and Sweden and San Diego, and I got somebody there in Las Vegas, and
Steve, maybe you don't know, but actually, Per is sitting next to a dime. Those books are actually Pyro books behind him.
I like the firecracker string in the back there. Good shot.
Yeah, it's a large collection, and it's almost not only books about pyrotechnics and explosives, but mostly there's something about chemistry too.
That's awesome.
It's great. No, it's perfect. It's absolutely perfect.
And on the floor, maybe you can see there's some bags there. That's where I keep all the antique stuff.
Very good.
Because I don't have a shelf room at the moment.
Yeah, myself, I have just brought some of these, books here. I mean, about let's see, those basic pyrotechnic books, since I have them here, but we didn't need them.
No, it's cool. Yeah, I mean, you had plenty to talk about, so we weren't hurting for things to talk about, and we ran. I think it ran about an hour and 15 minutes. I'd have to go back and look.
Hour 20 at least.
Yeah, about that.
Okay, but
it was worth it.
But it's good to know that we didn't get chopped off at 1 hour too.
Yeah. Gentlemen, I just would like to say thanks a lot. I need to go home to my family because I did this at work, and there's a long drive, not a long drive, but almost an hour drive home. But Dominykas, if you are going to give this talk about blue strobe, I mean, I'm not that into it, but if you need a sidekick, I can be there, just to help you out.
I think I can even ask right now. I mean, I would be happy. It would be great if you could join once more, because even for me, it was much more interesting to talk, having someone on the side, and even you see we had some technical difficulties. So I'm really glad that you joined. So if I were to do about the blue strobes, I think, you can also join.
Yeah. We could probably also, and it's great because at Pair you give a really nice human element to the thing that helps interpret this stuff. So that, not that Dom, you're a robot or anything, but it's very good color to it. And if we do that, I'll check in with Eric McCaskey and Chloe Jennings White and see if they might want to join in on that. It'd be a little tricky to get Chloe because of resources there, but that might be handy. I'm always looking for, putting the right people together in the right conversations. So we'll see how that
would be great.
Okay.
I need to go home. So thanks a lot, and I hope to see you again.
Bye, Pear.
Okay.
Bye, Pear.
Okay. Bye.
Bye, guys.
Bye, Dom. Thank you so much.
Yeah. So, well, I'm still here. So do we have something to discuss, or because I'm already a bit tired?
Sure. Where do we send your check?
Yeah.
No, that's good. Bob, you're still there? You have anything to say?
No, other than the fact that I think this was definitely worthwhile. And I kept flashing on studies like this on much more difficult topics that I recognize the difficulty, and that would be glitter.
Yes.
Yeah.
Sorry. I'm like, yes, please. All of that. I loved today, by the way. I had such a great time watching. It was awesome. I want more of this, more technical.
Yeah.
Yeah, I'm very happy to hear that. Thank you.
Yeah. Actually, Bob, going, say technical or difficult, but, going back to going all the way back to the beginning of your glitter work would be just a fabulous review. Just having you do that, and also we could actually use it to promote this this green book.
Well, I don't want to promote that green book too much because I'm working on a second edition.
Oh, I know, but it helps. It helps keeping Cardwell energized too. So it's all good. All right.
Well, thank
All
you.
right.
Thanks, everyone.
Thank you so much. I haven't had breakfast yet, so I'm going to do that.
Thanks, gentlemen.
Yeah.
Thanks,
Yeah.
Bob.
Okay. See you, Brooke, Bob, Dom, and
Okay, so I guess we'll talk later on about let's see if we have plans for other seminars, and I would definitely like to attend Bob Winokur's seminar.
Oh, yeah.
Yeah, he gives a good seminar. Very good. Okay, very good. All right, I'm gonna say bye for now, and thank you again, and we'll be in touch.
Talk to you guys later.
Thank you, guys.
Bye.
Bye,
Thanks, guys.
gentlemen.
Till next time. Bye-bye.
Mhm.